Okay, problem 10.7. Consider the quadratic function f. That is a quadratic function here, and Q is a symmetric positive definite as usual. And suppose we have a matrix D, which is of size n by r. So, and it has a rank r. So that means the number of columns cannot be bigger than the number of rows. So it should be some tall matrix like this with n rows and r columns, and r can be as large as n, but cannot be larger than n. And let's say x naught is some given scalar, given vector. Then let's define a new function phi, which is from r to r by this. So for every given r-dimensional vector a, it maps to a scalar, and that scalar value is given by this f function here. So I want to show that the phi is also a quadratic function, and it has a positive definite quadratic form, meaning that the quadratic matrix should be, the matrix in the quadratic form should be positive definite. Okay, so we can just do that by a straightforward computation. The phi a is this, but this f is a quadratic function as we showed before, and just expand that, it becomes this. And then we can combine terms, and eventually we arrive at this form. So now actually both of these two terms combined together is the linear term. But since for quadratic functions, we're only concerned about the matrix for the quadratic term. So that is the matrix here. Okay, so you can see this is the matrix, and they have the AA transpose on two sides. And the question is to show that apparently this is the quadratic function for A, but now the point is to show that this is the positive definite matrix. Well, to show that is so as we said, the Hessian should be just this D transpose QD thing. And to show that it is positive definite, we just need to show that this, when you multiply the same vector A, any vector A, to both sides, this should be greater than or equal to 0, and this is equal to 0 if and only if A is equal to 0. Okay, first of all, we multiply this by A on the two sides. We combine this dA and this D and A together, so they'll form this 2 accordingly. And then this is just the square Q norm of dA, right? Square Q norm of dA, and that should be greater than or equal to 0. And because Q is positive definite, we know that this will be equal to 0 if and only if the dA equals 0. Well, when D is a matrix, it's a n by r matrix of rank r, that means the D has a full column rank, meaning that the columns of D are linearly independent. Okay, the columns of D are linearly independent. So if you have dA equals 0, then that means you're making a linear combination of the columns of D using A, components of A as coefficients. You get 0, then the only way that can happen is that the coefficients are equal to 0, meaning that the A is equal to 0. A is a 0 vector. It's r-dimensional and 0 vector. That means if and only if A is equal to 0. So this proves that this is equal to 0 if and only if A is equal to 0. So that means D transpose QD is positive definite.